And then we also have a single E. And this over here, is there a, okay, this over here is inducing a moment PE. Okay. The vector, moment vector is pointing that way. So this is under compression. This side is under tensile. In terms of stresses, okay, not so compress stress. This side is in tensile stress. Okay. So we know that this structure will buckle. Okay, we know the deformation, it will look like this. We are aware of that. Okay, right? So now, currently, we have a different problem. Not a different problem. We have a structure now, right? I'm trying to, okay, we have a structure that looks like this. Right? And then we have our, I'll draw, we have a beam. Right? And then our structure, we have a plate on top. Is it a plate on top? Yeah, we have a plate on top. And then we are given, we have a load of 130 kilonewton. And we have another load over here of 50 kilonewton. And then if I were to draw our geometric centroid, right, coming down from here. And we have two distances now. One is 120, the other one is 80. Okay. And we are aware that this is, right, this is rotation about X, right? So this is also buckling about the X-axis. Okay, so they did not say any restraint about buckling in the X-axis. Okay, so it will buckle in this way, right? So we know again the formula that we're going to use is again stress max, and this is equal to P over A, right? 1 plus by EC over R squared, and then you have secant pi over 2, and then we have square root P over PCR. Okay. Now, then we look at the different plane now. Okay, so now we are going to look at the XZ plane. And this is rotation about Y. Okay, so we are going to look at the XZ plane. And then buckling about the Y-axis. Okay, we have to be really, really careful down here, okay? We have to be very cautious with this. So now if I'm going to sketch that, okay, so now the view changes. Okay, so now the view, so now again, we have our beam. Okay, and then we have our geometric centroid. And then because of how the structure is orientated, this is our web. The dotted line, this is our web. There is our web. And if we were to look at the load is coming down vertically. And this load is coming down vertically is 130 times 10 to the power 3 plus by 50 times 10 to the power 3. Right? It's in line. Okay. So if this thing were to buckle, it will be buckling this way. And if you were to focus on the curvature, right, the curvature and the transformation curvature are the same. So this is buckling about the y-axis. And at this stage, the problem say that what? Fully brace against buckling about the y-axis. So i.e., no buckling. Buckling will not occur about the y-axis. Okay, we have to be careful down here. Okay, are we clear? Okay, we miss this out, then we are going to have problems. Okay, so now we are going to focus on this formula over here. Okay, we are going to focus on this formula. Okay, so the first thing we are going to do is I like to determine what is our P, right? And then what is our E, right? And our P and E, P can only be one value. Okay, E also can be. So how is the loading system over here can be equal to what's happening on the left? Can it be described by a single P and by a single E? Okay. The diagram on the right hand side over here, like I underline, you have two P and you have two E value. Okay, so now watch here. So we know, right, over here. Now I'm going to draw the wait, let me see. Is it better to draw, or if I have an image? I think I'm going to copy the image and then put it there. That's what I'll do. Bear with me. Okay. Okay. So I'm going to draw our transformation. This is Z. This is Y. Rotation X. Okay. So we know that the PZ will be equal to, so the PZ is the axial load, will be equal to 130 times 10 to the power 3 plus by 50 times 10 to the power 3. So the PZ, okay, that we have is equal to 130. Okay, 130 plus 50 is equal to 180 times 10 to the power 3 Newton. Okay. So the next thing that we want to calculate is we are going to calculate, so I'm going to call this point A. Okay, point A. We're going to call this point A. So anything that is anti-clockwise is going to be positive. Okay. So moment about point A will be equal to, so I'm going to take the centroid down here as the center. Okay. Because I know the distance of 120 and 80 is from the I'm going to change the color, is from this red dot, right? So this will be equal to 130 times 10 to the power 3 multiplied by 0.12 plus by no minus, okay, minus 50 times 10 to the power 3 multiplied by 0.08. So now the moment, because the 130 and the 80 are fighting against one another relative to the geometric centroid. Okay. So 130 power 3 times by 0.12 minus by 50 power 3 times by 0.08 is equal to 11600. Okay, or 11.6 times 10 to the power 3 Newton. Okay. So we are aware, right, that the moment will be in this direction, and this will be equal to moment at point A. Okay. Right. So when that's the case, we know that there's a P coming down here. The PZ now is equal to 180 times 10 to the power 3. And we know the moment of A is 11.6 times 10 to the power 3. When that's the case, okay, we can now find this distance, which is equal to E. Okay, so therefore E is equal to 11.6 times 10 to the power 3 divided by 180 times 10 to the power 3. So 11.6 power 3 divided by 180 power 3 is equal to 64.444 times 10 to the power minus 3 meters. Okay, I hope this makes sense to all of you, right? I will repeat the analysis again. I'll repeat the analysis again. Okay, watch here. Okay, so we know we have two loads. One is 130 kilonewton. Okay, one is at 130 and a distance of 120 or 0.12 meters. And the other one is at 50 multiplied by with a eccentric distance of 80. And we know moment is equal to force multiplied by perpendicular distance. And we know the moment due to the 130 multiplied by 80 will be higher. That's why the moment at point A will go this direction. So that's where I declare, or I'll do it this way, it's clearer to you. When the moment at point A going in this direction is positive, and this is relative to the geometric centroid. So that's where we have 11.6 times 10 to the power 3. With that, we know that the axial load is equal to what? 180. Okay. So you just take 11.6 times 10 to the power 3 divided by 180, and that's it. That is equal to 64.444 times 10 to the power minus 3. Okay. And you have to get this right. Okay, this is important. Okay, or not is confusing. Why we are doing this is because this formula over here, we are only allowed a single value of P and a single value of E. We cannot say that, okay, we're going to calculate deflection due to the 180, then we calculate the deflection for the oh god, for the 50, and then we sum them together. No, it does not work like that. Okay, you have to be very careful. Okay, so what we have is we know P. Okay, so now we know P. Okay, we are aware with what of P, and we know what is our E. Okay, so next we have to find our PCR. Okay, next we have to find our P. So P we know already. So next we have to find our PCR. So if we were to acquire our PCR, Hold on. Okay, so if we were to